26th tutorial of FIR on ping. Before we move into what we will be covering in this tutorial, let us recap. Previously, we had looked into basic sequences or basic mode of FIR IP, where we explored N channels and N data paths. Now, we will be moving on to the advanced mode of FIR IP. I'll introduce you to what the concept is and what do symbols like P41, P42, P43 and P44 mean. We will look into software and hardware executions of P41 with one coefficient set and also two coefficient sets. I would also like you to independently try implementing P41 with two paths and two coefficient sets. Natural question to ask would be, what is an advanced mode and how is it different from a basic implementation? Well, according to the FIR product guide version 7.2, it is defined as the list of predefined interleaved data channels or sequences or patterns from which multiple patterns can be selected during core customizations. This might temporarily go through your head or above your head, but let us look at the further information given to help understand the previous definition better. The core, while being configured, generally supports one channel with sample frequency of fs. But with the same hardware resources, I can now support two channels with fs, with each channel working at fs by 2. Similarly, 4 channels can be supported if the sample frequency drops down to fs by 4. Similarly, another configuration could be one channel working at fs by 2 and two channels working at fs by 4. All of these configurations are always predefined and can be used one after the another. Let us look at some sequencing examples to understand it better. P40 or one channel working at 1 fs. This is the basic implementation we have been doing all along, where one channel is being used at fs or sampling frequency. Let us look at the sequence P41 or two channels working at fs by 2. Over here, what P41 means is that 4 channels are being used with one data path each, but only 2 signals are being filtered. What I mean to say is, the FIR core remains 1, the data path also remains 1, but instead of 4 signals being filtered via 4 channels, I am only filtering 2 signals spread across 2 channels, i.e. channel 1 and 3 will be filtering one signal like A, which has input A, and channel 2 and 4 will be filtering signal 2, which has inputs B1 and B2. This happens across 4 clock cycles. So let us say on the very first clock cycle, my FIR core behaves like channel 1 and will filter input A1. On the second clock cycle, the FIR core will behave like channel 2 and filter input B1. Instead of going and introducing a third signal, on the third clock cycle, my channel 3 will now take input from the first signal's second sample and filter that, or A2 will be filtered. On the fourth clock cycle, B2 will be filtered. Going back to the sentences above, over here, what I mean to say is 2 signals are being filtered over 4 clock cycles over here, and channel number 1 and 3 handle the filtering of signal 1 or the first signal, and channel 2 and 4 handle the filtering of the second signal. How do we know this? Well, the filter coefficients need to be set in a particular way so that the filtering takes place correctly. this coefficient set? Well, there are 4 coefficient sets that need to be used here, but in an interleaved pattern. Let's say my signal 1 needs to be filtered via a low pass filter. A low pass filter in the coefficient file or the vector corresponds to set number 1, while signal 2 needs to be filtered via a high pass filter which corresponds to a coefficient set 2 in the COE file or the vector. Now the coefficient sets that need to be placed are 1 in the format of 1 to 1 2. So at every first and third place I have the same low pass filter, and at every 2 and 4th place I have the high pass filter. This is done as the first and the third channel have the same input signal and coefficient set, while channel 2 and 4 have the same input and coefficient set. This makes sure that the input is filtered via the same coefficient set. Now let us look at sequence P42, where 2 channels are being present, one working at fs 3 by 4 and the other working at fs by 4. Over here my input would look over 4 clock cycles would look like 0 0 0 and 1. Thus again 2 signals are being filtered via 4 channels just like above, but now they are being filtered at different rates. Now channel 1, 2 and 3 will be filtering the first signal and channel 4 will be filtering second signal. Thus naturally coefficient sets need to be corresponding to the same pattern. So set 1, 2 and 3 need to be of the same kind, while the fourth can be different or the same depending upon the requirement. I would ask you all to try implementing a simple P42 with one coefficient set. Similarly, P43 and P44 are also interleaving patterns that exist and will be explored in upcoming tutorials. But patterns also exist for 4, 6, 8, 12, 16, 24, 48 and 64 channels only. Each of them have their own defined pattern and can be used one after the other. The lowest number of channels for which advanced mode can be implemented for is 4, while the maximum being 64. Each of them can have their own number of data paths too.
With the implementation of tutorial 6, first we will implement the P41 advanced channel sequence via one coefficient set. Then we will move on to the second coefficient set. Let us start by creating our block design, where we first add our zinc IP and run the block automation. Next step is to enable our ACP port and disable all the peripheral pins. Next we add a DMA. Now in this, even though we start with disabling our scatter gather engine and changing of the width of the buffer length register to 23. Now that we have come to the memory map data width, for advanced channel sequence the number of bits doesn't change. My input for P41 is 0101 over 4 clock cycles. So that would mean that I have only one data path, which means 32 in both memory mapped and stream data width. And next the max burst size goes to 256, allowing of unaligned transfers and changing the max burst size to 256 in the case of right channel. Next, let's configure our FIR IP, where we first let us use the source as vector again. Copy a, let's say, a high pass filter over here. Actually, let us just stick to the low pass filter we have been doing. and copy paste it over here. As you can see, there is some sort of error, and that error is that there is a semicolon at the end of the coefficients. Once we have removed this, there is no longer an error anywhere inside the coefficient vector, so the Vivado does not give us an error. The number of coefficient set currently is 1, and the number of coefficients per set is 27. That is correct. The filter type is still single rate. The channel sequence now goes to advanced. As soon as I click advanced, the minimum number of channel goes up to 4, and currently I will be implementing P41 or 2 channels working at half fs, and since I have to implement only P41, my sequence ID list will only contain P41. In case I wanted to implement P41 in the first clock cycle and then P44 in the second clock cycle and then circle back to P41, I would have a sequence of P41 and then P44. But since I want to implement only 2 channels at 1/2 fs, I will just write P41 in the sequence ID list. The number of paths remain 1 over here, and the input sampling frequency is 100. The input data width is at 32. In the interface tab, my T last is at packet farming. I will enable output T ready and add control signals like A reset N. Next, we run the connection automations. Now let us look at the input and output interfaces. The input to the FIR compiler consists of 32 bits. Same goes for the M-access or the master interface memory map to stream of the DMA. Thus we connect it via the interface. Now when it comes to M-access data, as you can see, sorry for the interruption, moving on with the addition of the slice. We have 48 bits over here, but we need only the first 32 bits. So I have a DN width of 48. I will go down from 31st bit to the 0th bit, making my D output width to be 32. I will add the slice over here, connect the M-access data T data to the slice, and I will add a width converter or a stream data width converter along with it, as we need to change this 30. Oh yes, I'm really sorry, we do not need the width converter. We can just directly connect the slice to the S-access S2mm T data, which is also of 32 bits. Next we connect the T last. Next we connect the T ready of the FIR compiler to the T ready of the S-access S2mm. So will we connect the T valid. And next step is to run automation connections for all of them. And after this, we will connect the A reset ends and the A clock. Look around if you can see anything that has not been connected. I will now regenerate my layout and validate our design. As you can see, we find a critical warning that says S-access S2mm interface is unconnected. This means that the interface over here, this particular interface, is unconnected. But we have connected these signals individually, so there is nothing to worry about over here, and we can go ahead and ignore this warning. Next, let's generate output products. After the output products have been generated, we will create an HDL wrapper. And next step is to generate a bit stream. As you can see, the synthesis and implementation have been queued, and the generation of bit stream will start soon after the implementation and synthesis are done. As said in tutorial 5, we will just look at the changes in each code rather than going through the entire code, as most of the blueprint of each of these tutorials software or Python codes remain the exact same. We start with the imports and load the bit stream, use a sampling parameters and set them. We create two signals over here. One is 90 and 10 megahertz, and the other is 30 and 90 megahertz. The first signal is named A and the second is named B. We have coefficients being defined over here. Next, we use time domain convolution, or we do time domain convolution through a function known as lfilter inside the scipy from scipy. Then we have frequency domain multiplication of A and B. Next, instead of if you would remember our tutorial 4, we were interleaving in parts of 8 due to 4 paths. Since over here I have only one path, I have an interleaving of just 2, one for channel A and one for channel B. Next is we copy that input data into the input buffer, send it to the hardware, wait for the executions to finish and end our time. Next, we print the hardware execution time and de-interleave our outputs. After the de-interleaving is done, we convert all of the outputs and inputs into frequency domain, as it is easier to visualize, and then plot them. Once you plot them, let us look at our test signal. We have 10 and 90 megahertz, 30 and 90 megahertz over here again. So according to our low pass filter, we should be able to filter out the 90 megahertz in both of these test signals. Let us look at the input. Over here we have 4 peaks at 10, plus 90, minus 10 and minus 90. Similarly, we have a 4 peaks at plus 30, minus 30, plus 90 and minus 90 again. After this, my time domain convolution gave the exact output as a theoretical guess that the 10 megahertz will be allowed to pass while 90 will be attenuated. Same goes for input B. 30 was preserved while 90 was attenuated. Same goes for our frequency domain convolution for A and B, where my 10 and 30 megahertz have been preserved while the 90 in both cases have been attenuated. Same output is given by our hardware. Again, 10 and 30 megahertz have been preserved while 90 megahertz in both cases has been attenuated. Let us change our 90 to, let's say, 95 over here, and I change my 10 to, let's say, 20, and I add a 30 over here, and let's say a 20 over here. So theoretically my 20, 30 in both cases should be preserved, while 90 and 95 over here should be attenuated. I have my 6 peaks, one at 20, one at 30 and one at 90. Sorry, this is 95, I believe. Yes, I have 95 in the first signal and 90 in the second signal. Again, we have one peak at 20s, one at 30 and one at 90 over here in input B, and 95 in input A. The time domain convolution has attenuated the 90 and the 95, while it has preserved 20 and 30 megahertz. Same goes for the time domain convolution result for signal B. 20 and 30 have been preserved, 90 has been attenuated. Same is the case for frequency domain convolution. As you can see, 20 and 30 have been preserved, 95 has been attenuated. Same case for signal B, 20 and 30 have been preserved while 90 has been attenuated. As you can see, there is a slight presence of the signal at 95. This is due to the fact that 95 is significantly close to our Nyquist rate, which is currently 100. Now we have an hardware output A that has preserved frequency 20 and 30. Same in terms for hardware output B, where 20 and 30 have been preserved. Instead of redoing the design again and again and following the same exact steps, let me just show you what are the changes and the configurations I've done per IP. Beginning with the zinc IP, I have enabled our ACP port and disabled all the peripheral pins. In this particular tutorial, we have been implementing a P4.1 implementation with one data path. So I have 32 bits due to one data path. Disabling of the scatter gather engine. The width of the buffer length register being 23. Max burst size being 256 in both read and write channel, and the allowing of unaligned transfers. Apart from this, we have configured in FIR compiler with 4 coefficient sets for P4.1. These coefficient sets are one after the other. As you can see, the first coefficient set is over here. The second is from here until here. This is a low pass filter, while the one before it was a high pass filter. Same goes over here. Alternatingly, I have put in high pass and low pass filters. The number of coefficient sets over here are 4. The number of coefficients per set are 27. In the channel specification tab, I have selected advanced channel sequence. So my number of channel automatically goes to 4. What the sequence inside this advanced implementation I have used is P4.1 with one path and an input sampling frequency of 100 MHz. In the implementation tab, I have increased the input data width from 16 to 32. In the interface tab, I have put my T last on packet farming, enabled output T ready, and in the T user section, I have selected channel ID field for input and output, and my configuration channel option shows my synchronization mode is on packet and the configuration mode is by channel. What I mean is, by doing or following these configuration channel options and T user, I have the length or the range of my S-axis config T data goes from just 0 over here. Let me show you. If I put them on not required, and this on vector and by single, then the range of my S-axis config T data is only till 0. But in case I use input to be channel ID field and then my synchronization mode being on packet, as my T last is also on packet, and my configuration being via channel, or it means that I will be able to use different coefficient sets per different channel and not according to one single coefficient set being used. When I do this, my field select line appears of 4 from 0 to 3 or 4 numbers. This is how I have configured my FIR compiler. The input to my FIR compiler is 32 bits and so is the DMA of 32 bits. Sorry, the input is from the M axis, MM2S. Since they are both of the same bit length, I have connected them via the interface. While the output I have over here is 48 bits. Hence I have used a slice, as you can see over here, a slice that takes only the first 32 bits and gives them to the DMA. Next I have correspondingly connected the TLAS, TREADY and TValid signals from the slave interface of the DMA to the master interface of the FIR compiler. At last I have taken a binary counter that goes from 0 to 3, as that is a field select line range, and gives it to the S-axis config T data. Then I have a constant of width 1 and constant value 1 that is given to the S-axis config T valid to ensure that the valid is asserted while the binary counter's output is on the line. This is our valid design. Let us validate it to ensure it is correct. As you can see, the only error I am receiving, or a warning that I am receiving, is that the interface is unconnected. This is due to the fact we have individually connected the signals or the lines rather than connecting them via interface. You can go ahead and ignore these. Next step is to generate output products. As you can see, the two critical warnings over here are of the width mismatch, that says the only lower bits will be connected, rest will be left unconnected, which is exactly what we want. Hence we will go ahead and ignore these warnings and move on to creation of HDL wrapper. Our HDL wrapper has been created. Now we will go and generate our bit stream. In the bit stream, my synthesis and implementation have either started or are in queue. Once these runs are done, the bit stream will be generated. The two-set implementation of tutorial 6. As you can see, my generated signals are A and B over here, with 20 and 95 megahertz in the first signal A and 30 and 90 megahertz in the second signal B. I have interleaved these data input and then copied them into the input buffer and send it to the DMA. Wait for all the executions to be completed and end our timing over here. After the calculation of the timing, I have de-interleaved my outputs and FFT'd them, or fast Fourier transformed all of my inputs and hardware outputs, and plotted all the 4 frequency domain responses. And these are as follows. As you can see, my input A over here, it was a combination of 20 and 95 megahertz, while B was a combination of 30 and 90 megahertz. Over here I have all the 4 peaks, but in case of output A, HPF or a high pass filter has been used, thus my 20 has been attenuated, while in case of output B, a low pass filter has been used and the 90 megahertz has been attenuated, while 95 in my input A and 30 megahertz in output B have been preserved.